Welcome everybody to tonight's meeting of the Astronomical Society of Edinburgh. I'm sorry you've got me again, but Mark is taking a well-earned holiday, so I'm just stepping in for tonight. So I'll be talking about what's coming up, and then we'll move on to Professor Giles Hammond, who's going to talk about the photometry of short-period asteroids. And that will be followed by Alan Pickup, giving us a view of the sky in July. So, first of all, can I ask members perhaps unmute and welcome Chris Roper, our 141st member. The membership keeps climbing. So, welcome to Chris. You're tuning in. And a ridiculously cheap offer. You can join the society for only £30 a year. And if you're in full-time education, that's on a learning side as opposed to a teaching side, or you're a concession and old like me, it's only 15. All the details of which you'll find on our website. You can follow us on Facebook, on Twitter, and I think virtually all our talks over the last lockdown period, nearly 2 years, I guess now, are on our YouTube channel. So feel free to access those. So, what's coming up? Well, on the 16th of July, we've got a bit of an end of term report, come pub quiz, come holiday chat. It's members only. You can choose to drink or not drink to your heart's content, as you'll be supplying it. On the 7th of July, it's been decided we will have another imaging and observing group meeting, again, members only, before we start our August break. When we come back, hot off the press, the 3rd of September will be Super WASP, and then on the 8th of December, it will be the imaging and observing group again. On the 17th of September, a slightly different angle, we've got exploring astronomy and space through philately. And on the 1st of October, we're going to talk to Mike Shaw about astro landscape photography. So if you want to know how to take those great pictures of the Milky Way and a static foreground, then we'll tune into Mike Shaw on the 1st of October. All the ones at the moment that are shown will be presented on Zoom. We are looking still at how we mix that, blend that with physical meetings. But more of that as time progresses and the various tests are carried out, and we see just what we're capable of doing. So with that, I think I'm going to hand over to Professor Giles Hammond of Glasgow University. So over to you, Giles. I'll stop sharing and allow you to do the same. Giles, you're muted.
Yeah, thank you. That classic phrase of the last year, you wouldn't believe how many times I mute myself. Apologies, my video sometimes freezes, but I can still hear you, and you should be able to hear me still. I guess, as Andrew said, well, you've got me again as well. So it really is a pleasure to be talking to the society. I don't know if this is maybe the 3rd or 4th time I've given a talk. Today, I wanted to do something a little bit different. So this is absolutely nothing to do with my area of research. So of course, I work on gravitational waves and building MEMS gravity sensors. But this talk is really motivated by some work that we did over the sort of last year of teaching at University of Glasgow. And I just wanted to share some of the work that we did because it was actually quite a fun kind of project. And this was all about imaging asteroids. So it's about doing photometry. So I wanted to give a little bit of background to the project. You know, why on earth were we doing this in lockdown, and how we actually went about doing it, because actually we couldn't use our telescope in Glasgow because that was unavailable for access. So we had to kind of change our plans and do some work with a remote telescope in Spain. Talk about a little bit about the imaging work. So of course we all know about probably bias, darks, flats, and stretching of images. So it's got some kind of nice kind of imaging aspects, this talk. And then of course you need to find the asteroids. So we did quite a lot of work on plate solving. And this is the great fact that you can upload your images and it will tell you where you're pointing in the sky. And then of course, how do you generate the light curves? Well, we have to do some data reduction. We have to look for some calibration stars because we don't know the magnitude of the objects. So the way that we do that is we use aperture photometry. So some of these tasks you might have seen before actually, but I'm going to show how we sort of took it from the sort of very raw data all the way to hopefully a finished light curve. And of course, it's work in progress. We ran these remote projects for the first time this year, and I'd say they actually worked really well. But of course, there's some things we'd like to do better next time. And I'll sort of maybe give you some hints at the end of how we might change things. Anyway, why did we do it this way? Well, we have quite a large astronomy program. So in our sort of third and fourth year, so we have students doing physics with astrophysics. They have to do an astronomy lab projects, and we have astronomy and physics students. And these projects are run in the second semester, and there's typically about 100 students. And we give them an option of either doing a practical or computational lab. Now, of course, in these sort of times of non-face-to-face teaching, doing computational work, I'd say was relatively easy. If you've ever tried to debug a student's code remotely, you might think it's not so easy. But still, it's much easier than instrumentation work or practical work. But we still wanted to actually give the students this sort of feeling of, you know, what it's like to take your own data and to actually analyze your own data. And it turns out actually doing things with a remote telescope, it probably looks a lot more like, you know, how a sort of modern astronomy kind of postdoc or staff member might work. You know, you sit kind of remotely in a control room and you tell the telescope where to point, and then you just get the frames which you then have to analyze. So shown here are some of the projects that we offer our students. So as I say, we've got computational ones and we've got practical ones. And I mean, I could spend the whole time talking about the projects because they're really quite good fun. But you can see here there's a wealth of sort of computational activities. So looking at slowdown of the Crab pulsar. So looking at the neutron stars spinning down with time due to electromagnetic or gravitational wave braking. We do some Newtonian analysis of planets, so we can actually generate our own little solar system simulator. We analyze gravitational wave data, so this is looking at real observations from LIGO and filtering the data, or using some of the Dwingaloo survey and looking at H1 lines and actually looking at the rotation curve of the galaxy. So we still run those as normal. The practical ones kind of took a little bit of a hit because we realized we couldn't actually do a lot of them. So because we didn't have any face-to-face teaching, we weren't able to open the observatory. So this caused us a little bit of a headache around Christmas time. So looking at the different projects that we run, so these are the practical ones. So we do a really nice lab on high resolution imaging. So this is, of course, looking at lucky imaging. You take lots of frames and you have a metric that tells you, you know, what's a good frame, when is there not much scintillation or aberrations in your optical system, and you just take the good frames. So we couldn't run that just because, although it only really requires a video camera and a telescope, the amount of data that you actually physically take just makes it very hard to operate a remote lab. So we decided not to do that one. We have a nice project on advanced spectroscopy. So this is looking at, so for example, you can look at Jupiter rotation, or you can look at spectroscopy of the sky, and you can look at the solar bands and the absorption lines. We couldn't do that because there wasn't easy access to a spectrometer. We have a project on solar limb darkening. Well, that was out because then you need access to a solar telescope, which is remote, and that was difficult. I was running a project on Roma delay, which I think I've talked about at some point. And this is about looking at using eclipses of the Jovian, or could be Saturn satellites, or even Uranus, and by looking at the time delay of when you expect the transit or the eclipse to occur and when you actually observe, you can estimate the speed of light. Well, we couldn't really easily do that, partly because Jupiter's, I mean, it's easier than last year, but it's still a little bit of a challenge, and you don't get too many events. So we decided to not do that one. And then the final one, which is another fun one, is you actually build yourself a little magnetometer using a compass, and you can measure solar storms. But practical work was difficult. So the one that sort of stood out was, well, we could actually do something with asteroid light curves, because this requires access to a remote telescope, which is of course possible, and a CCD camera or a CMOS camera. So we actually use a CMOS camera really. So this is the one we decided, well, if I had to run a project, let's try and do that one. And of course, you know, what are we trying to look for? Well, we're trying to look for the fact that asteroids have different rotation periods, and as the asteroid rotates, you get modulation in the brightness. And that could be a number of factors. It could be due to the albedo of the asteroid. So maybe there's a sort of lighter bit and a darker bit. So as it rotates, you get some modulation. But it might also just be because of surface area. And what you see is typically that in terms of modulation, it can be as high as 0.1 of a magnitude. So we thought, well, actually, that's quite an interesting target. And we tried to run this project previously as in Glasgow, and the sky quality was never really that good. So light pollution causes real challenges, and if you get a lot of reddening as the asteroid changes its altitude, it makes it rather hard to run the project. So we thought, well, actually, if we do a remote telescope, we could get a good quality sky. Of course, there's different rotation periods, and there's really fast rotators. So there's ones which are sort of up to 0.1 of an hour, so you can have many oscillations a day. And there is a limit actually, and the limit usually comes from the fact that the asteroid can't hold itself together. So this is quite a strong cutoff where you don't get really fast rotators, or perhaps they don't last for very long. We were looking at typically the larger asteroids, so more than 1 kilometer, because they're bright, but they also have rotation periods of a few hours. So if it's 8 hours, then actually over the course of a night, you could in principle get an observation of the full period, and then you do that on a consecutive night. If you see the same, well, you think you found the light curve. And of course, I should say, you don't have to limit this to asteroids. You can do this with exoplanets, although typically it's a little bit of a harder challenge because the magnitudes are even smaller. So it might be 10 times smaller than an asteroid modulation. So we thought asteroids were a good target. But it turns out we've sort of lucked out, because 2 of our demonstrators have been setting up a remote telescope. So one of them, he went through our graduate program, and he's now a pilot for British Airways. So he used to fly a lot of the time out to Sevilla, and he sort of started to kind of work with what's called EI, which is a Spanish sort of remote telescope hosting facility. So they've essentially got a whole bunch of, well, you can see on the Google map, you can start to see some of the runoff sheds there. They've got a lot more of them now. I don't know exactly how many telescopes they've got now, but it's quite a few, probably more than 20, I would guess. So they have the option of, you can host your telescope. So the two of the demonstrators had been sort of trying to set up this remote observatory. So they said, well, you could use that, but we decided that we'd buy a new camera, large format CMOS camera for the observatory, and we got that shipped out to Spain and put on the back end of the telescope. Sky quality is much better than Glasgow, and well, we thought the weather was much better. Turned out, you might remember that in Spain there was this surprising amount of snow that had fallen at some point, and so the observatory was shut for a little bit. Anyway, the sky quality is pretty good there. There you can see some of the sheds. Well, my estimate of 20 telescopes is probably rather an underestimate if you see that each of those is hosting a telescope, and there's maybe 6 or 7 of these sheds, so you can actually essentially buy some space where you can put your telescope. And there's an observatory manager who sort of looks after the telescope and can help if there's things that go wrong. There's webcams there, so you can get access to this telescope. So it's actually quite a nice facility. So that was really, really lucky, and we, good facility to have. In terms of sky quality, well, you can all decide how we want to measure quality, but typically they class there as in Spain as a rural sky. So on the Bortle class, typically around 3 they have, whereas in Glasgow we're typically looking at urban or city sky, so we're 7 or 8. So we're clearly at a much darker location, and we have a better chance of consecutive clear nights. So while we set about the task of putting together the lab, and of course the way it works is that you've got 10 weeks to work with the students, and I ran this project for about 20 students. So we had them working in small groups, so they sort of take the data and then sort of get together and do all of their own coding. So this is the details, telescope and the setup. So of course there was a nice mount with absolute encoders, so you know where you're pointing on the sky. Of course, not so much of a problem because we can plate solve, but you'd like to know that if you put in the latest orbital elements of your asteroid and you point to the object, you're gonna find it pretty close to the center of the field of view. The plate scale was quite nice actually, because the full width half maximum is a few pixels, typically 4 to 8 pixels. So you are getting down to sort of 2 to 3 arc seconds. There's a set of photometric filters. So for some of our other observatory kind of activities, we were planning to run some sort of photometry of clusters. So you can look at the color of open clusters, and by looking at the color of the stars and how many there are of different sort of magnitudes as a function of color, you can make an estimate of the age of the cluster. So we did actually get some photometric filters, and we used the Sloan. Of course, there's all different kind of sets of filters out there. So you can have Johnson filters, UBV magnitudes, but we went for the Sloan, which are essentially bandied as GRI, and there's a Z. So it's roughly maps to green, red, and into the infrared. We bought this large format camera, so 60 megapixel. Of course, the frames, I did say that the data for the high frame rate video was quite large. Of course, a single frame of these cameras are still quite large, but much more manageable. And you can crop the images as well. So we worked a lot with cropped images. And then we had a short focal length refractor. So that coupled together gave a very nice imaging system. Well, we have to choose some objects, and I kind of, well, I sort of gave the students a little bit of a free rein, but I did try to give them a few boundary conditions so they wouldn't go off trying to observe 20th magnitude asteroids, because that's not going to work very well for their lab. They've got to end up with something that they can write up at the end. So we thought we'd go for reasonably bright. So here we're more than 12th magnitude, and that makes quite a lot of sense, because when you're looking for calibration stars, so you're trying to actually work out the magnitude of the asteroid, there's a lot of calibration stars which are in that sort of 15th to 10th magnitude. If you go too faint, then your catalogue has become very, very large. It becomes quite challenging. You don't want to download the Gaia catalogue to find your objects. So that was the motivation for the brightness. The rotation period, again, something that's short, so you can observe over the course of a night a whole rotation period in Spain. Circumpolars are visible from the observatory throughout the night. You don't want it setting, and ideally high in the sky. That's not always possible. And then a reasonable magnitude variation. And again, 0.1 of a magnitude is quite standard for asteroids. So that's a much easier target than something that's 10 times less than that. So we did settle on a couple of objects. So one was minor object 196, Philomela, magnitude 11, and then we also used 29, which is amphitrite, and this was 10th magnitude. Of course, it changes over the course of the observing period because the asteroid changes its relative position to the sun, but at the time it was around 10th magnitude. Well, just to look at Carte du Ciel, so there's a lot of asteroids out there. So those are the kind of two different captures. So here you see amphitrite. So this was sitting just in Leo at the time. With hindsight, it was okay, but At some of the time, it was getting pretty close to Regulus, and we're seeing a little bit of scattered light coming from that star on a 300-second exposure. But you can see here all these little red circles are asteroids. So there's, of course, there's lots to choose, and a lot of those are reasonably bright. So the students could have chosen many of them if they wanted. And then Philomela, just out of Gemini. And again, I've marked some of the other asteroids in the frame. But anyway, 2 is plenty. And actually tonight I'm only showing you data from Amphitrite, partly because that's the one I just had easy access to. I could have looked at Philomela as well, but well, time was against me. Okay, so this is the data. So of course we logged on to the computer, sitting at the remote telescope, and we could actually organize a whole sort of set of image taking. So what we typically do would be take an image in the green filter. Then we do some, we'd then change the filter, take another image, and then just cycle through that. And then by the time you've done that, 20 minutes later, you're ready to take another image in the green. So every 20 minutes, we got a new data file. And of course, because the orbital period is 8 hours, 20 minutes, third of an hour is absolutely fine for taking the images. We also took some dark frames in between, and just for sort of housekeeping to check as a function of temperature of the camera. As I said, full frame size of these images are 0.5 gigabyte. So we kind of sort of downloaded those after the course of the evening onto our local servers in Glasgow. We also, of course, took bias frames. So this is essentially the shortest frame that you can take, ideally 0 seconds of length. And this looks at readout noise in your CCD or your CMOS sensor. We took dark frames at multiple times. So we used 300 seconds for our image frames, but we weren't sure initially whether we might want to take shorter images. So we also took some different length dark frames. And then we took flat frames in the GR&I filters. And of course, those are to look for any vignetting. There might be dust on the sensor, any fixed pattern noise on the CCD or CMOS. And fixed pattern noise here means that pixels have slight different quantum efficiency, so they have this sort of slight different sensitivity. And then of course we averaged, I forget exactly how many, but it's probably about 20 of those frames to get the master bias dark and flat fields, which we then use to analyze. And this is our directory structure, and you can see there's full size images, and then we had a whole range. So we sort of cropped images down to 1000 by 1000. And typically we operated with 6000 by 6000, which is about half of the native size, so 130 megabytes an image. And that was kind of a trade-off between getting a good size of sky and getting enough calibration stars. We probably would have been better rather than just cropping, and that's a thing we should do next year, is actually just binning the data. So we could bin it, because it's photometry, you don't really care about the pixel size as long as you capture the image. So binning it would allow you to keep full sky coverage, but reduce the size of the image. Unfortunately for our students, they don't have the benefit of using AstroImageJ or PixInsight, which we all, I'm sure, love. And they are fantastic programs, but we have a requirement that our students learn Python programming. So we do that for vertical integration through the degree program. So they learn it in the first year all the way through to their 5th year. So we get them to do all of this analysis in Python. So they write their own code to do dark frame subtraction, bias frame, flat fielding. We don't let them use any other software. But of course, if you were doing a similar project, it's really easy to do this in AstroImageJ. But the key things are, you read in the data files. We've got to do the calibration. So we've got to take off the bias, the dark, the flat, or divide by the flat. We do some plate solving, partly because we want to know where the asteroid is. We find the asteroid, and then we find some standard calibration stars in the image, and that allows us to estimate the magnitude of the asteroid. So in order to do the image calibration, we use kind of this expression here, which is fairly standard. So here, this is a corrected image, or pixel, CIJ is just a pixel in the image. So this is our raw source frame. So we subtract the dark frame, and that includes the bias in there. So we just subtract the dark of the same length of time. And then we divide by a flat, which is bias corrected, although it doesn't really matter to bias correct because the count rate here is so low compared to the flat frame. So as you probably know, we typically sort of image the flat frame to maybe a third of the full world capacity. And then of course we multiply by the mean of f minus bij, and that's in order to just scale the image. So let me show an example of why we do that. I'm sure you know why we do it, but imagine we had a 16-bit image. So that means that black is 0 and white is 65,536, which is 2 to the 16. So if you image your flat field to about third the full world capacity, which is 23,000, let's just assume the bias was 100 because it's a low number of counts, maybe the dark frame 500, and then your source frame is around 5,000. So if you did this without correcting with this mean of f minus bij, then you just get 5,000 minus 500, so 4,500 divided by this really large number. And you divide that and you get 0.2. Now, unfortunately, if you do that in Python, then it thinks 0.2 is 0. So it thinks everything's black. So of course, what you have to do is you have to boost your image by the mean of the image. And when we do that, we get 5,000 minus 500 divided by the flat frame. And of course, because it's a single pixel, it's just the same number here. So of course, we just see 4,500. Of course, you could just say, well, why on earth didn't you just take your flat frame and just divide it by the median of the frame? So your maximum pixel, your mean pixel value will be 1, and it will go to 1 to 1.1 to 0.99 or 0.9. And of course, if you did that, you wouldn't need to multiply by mean of f minus b, which is the same thing. Anyway, that's what we do, and that causes the students endless confusion, of course, when you divide and then you see everything's black. It's all a learning process, and we then save our data in 16-bit format all the time. So then we get the full dynamic range recovered. Of course, we do stretch. So those of you who do astrophotography will be well used to stretching. Well, we only do linear stretching. We don't allow any non-linear stretching here because we're doing photometry. So we don't actually want to cause any weighting, which is non-linear. So of course, with stretching, you've got your image here at the top, and black is at 0 and white is 2 to the 16, so 65,536. But actually, a lot of your data, so this is a flat frame, of course, and it's got a minimum value of 13,000 and it's got a maximum value of 26,000. So when we stretch and when we do a linear stretch, then of course all we're saying is that the new black is 13,000 and the new white is 26,000, and we just sort of stretch that image out, and then of course we get this expression here. So we're using the full dynamic range of the screen, and we're just saying, well, most of the data, there's nothing above 26,000, so why do we need to even use it? And of course, what we don't do a nonlinear stretch, but you can do anything you want. So you could do a stretch that looks like that, and then you could sort of pull out the bright bits and vice versa. Although if you're doing photometry, that's bad news because it means that you've now introduced a nonlinearity into your system. Anyway, that allows you to explore, display your astronomical images on your monitor. And if you then do that, then this is what we get for our bias. So there's our bias. And of course, it looks a little bit grainy, but of course, remember, we've stretched this image. So white and black here are sitting between 411 and 413. So of course, the readout noise on these CMOS sensors, I mean, it's surprisingly good, actually. I mean, a few years ago, everyone would say, oh, don't want to use CMOS for this, sort of long exposures. But actually, it's becoming a pretty good technology, actually, compared to CCD technology. And you can see there, so this is the dark frame, and we've got a little zoom of the dark frame at the bottom here. So we're just stretching between 400 and 500 here. So of course, some of these are a little bit higher than that. I forget what the highest value. Some of those will saturate, so the real hot pixels will be a problem. But we can play around with that. So I get the students sometimes to do their own dark frame subtraction, and it doesn't always work quite well enough. So what we do also is we go hunting for sort of single pixels, which are just outliers, which are sort of very high pixel values, and you can sort of take those out and you can replace them with sort of mean pixels around. And of course, Astro Image Day and Pixel Insight are well used to doing these sort of algorithms. So hot pixel detection, because you expect that hot pixels are just going to be single pixel images, so you can generate your own pixel map to subtract if you want. So there's endless fun for them to work on. And there's a flat frame, which looks a bit awful, but of course, again, because it's been stretched, but there is some bit of, well, some unpleasant vignetting and darkening of the images. So we get around that by dividing by the flat frame. It's not too flat, but it's not too much of a problem for us either. So that's our image calibration. And then we go on to plate solve. So again, you want to know where you're pointing in the sky. And this can be very useful if you take just an image and you want to check the pointing of your telescope. So what you can do is you can, there's this sort of interface called astrometry.net, which is quite useful. And what you can do is you can upload an image. And of course, the image could be mirrored, it could be sort of rotated, and astrometry.net will kind of do a sort of fix of the different star positions, and it will tell you where you're pointing. And it will tell you the center, RA, and declination. It will tell you whether your image is skewed. It will tell you the plate scale in arc seconds per pixel. So it really is quite a powerful technique, and it gives you the idea of where you're pointing just for sanity checks, so you know that your asteroid is where you expect it to be. Now, when we use the Python interface to astrometry.net, we don't actually upload the full image because that just becomes rather too heavy for our server. So you'll notice actually that what we do is we find there's all these little yellow dots in the image. There's a better one later on. These are all stars that have been found by a stellar detection routine. So Python has this kind of nice routine that will look for stars depending on the brightness and the full width of our maximum. So it knows that a hot pixel is 1 pixel, but a star is typically 4 or 5 pixels for our imaging system. So if you tell it to look for sort of Gaussian objects of 4 pixels, it will actually find the stars or the stellar objects. And it just gives you, it just outputs coordinates, and then you upload those coordinates to astrometry.net, and you just upload a text file, which is much easier than trying to upload 130 megabytes of image. So we do it that way, and it works really well. And then, of course, you get your image back, and then you can plot the lines of right ascension declination. So now you've got a calibrated image. And that's a bit of a closer image of the bottom corner. So there you can see 10 hours, 13 minutes sitting up here. And there's these sort of yellow objects. So the yellow objects are things that the routine has found as stars. So it hasn't found them all because we put a threshold and we say, well, only find the one brighter than a certain background, because we don't want to find 20,000 objects. We only want to find 500. So these are all objects that get uploaded to astrometry.net to find the location. And then we've got these sort of blue and red circles, and the blue circles are calibration stars that we've identified. And then the red circles I'll talk about later. These are the aperture photometry circles. Okay, well, we need calibration stars. So what we do is we first of all find where the asteroid is. And again, another handy bit of software if you've never used it, JPL Horizons. It's fantastic. It's a tool that just tells you where objects are. So it of course sort of it's a minor planet database. And you can put in the data. So the observer, you can look for 29 Amphitrite, which is the asteroid we're looking for, using topocentric coordinates. So these are the latitude and longitudes of the observatory. You can tell it when you want to search, and you can get data every, well, you can get it every 30 minutes if you want, or quicker, and you can output in right ascension declination. And then what it does is it tells you the images I showing were taken on 10th of March this year. So there's the position of the asteroid, the right ascension declination. And good news, it's 10 hours, 11 minutes, which should be on that image somewhere, not on 10 hours and 13, but I'll show the bit where it's right in the center of the frame. and there's the declination of the asteroid. So then, because we know with plate solve, we know where in the sky we're looking, we know the right ascension and declination of the asteroid, we can now actually say, well, I know which one that asteroid is. And it's that one there. It's slightly off by a couple of seconds, and I think it's down to the fact that I just used the wrong time. So I was off in a little bit of time because it changed over the course of a night by 20 seconds in RA. So the asteroid moves, of course. So over one night, I'll show you in a minute, you can see it move between 3 hours or whatever. So you can now see there's the asteroid, object number 276. It thinks it's a star. It doesn't know any better. It just looks for stellar type objects, and an asteroid looks like a stellar object, of course. And then you've got a bunch of calibration stars, and we're going to use some of those calibration stars a little bit later. Not all of them are sun-like stars, and very few of them are sun-like stars, but we use sort of G-type stars to do our calibration. So that's the center of the asteroid fields, and that's our asteroid amphitrite. Well, I did just upload this to PixInsight. So if you put this into PixInsight, I always find it incredibly hard to find an object. You know, you're looking, of course, you can do blink analysis, and it's much easier to do that, finding asteroids with blink analysis. So there's of course, that is the asteroids. You'll see that familiar sort of 4 stars there, and the 5th one that looks like a little saucepan, but of course it's rotated. So endless fun trying to map things, but there's the 4 stars and there's the 5th one, so it's that little saucepan, so it's rotated. But you can see here the center, and the center here, well, it has moved. It's closer to this star in this frame, but of course, let me put you out of your agony. Let's do a blink analysis. So there you go. There you can see the asteroid. So that was taken at when it was at 9 o'clock 45 seconds, and that was taken at 11:09. So you can see that it moves across the sky. Well, it's just an asteroid. It's got orbital elements, so it does move relative to the background stars, of course. Again, it's a voyage of discovery for some of our students when they realize that asteroids move relative to the background stars, but it's all about learning in the lab, and it's good if they appreciate how you can actually see that these objects are moving over the course of one night. And of course, those of you who've done imaging, you always find these really annoying little trails, which are either due to satellites or asteroids. So of course, over long exposure, you can get a little bit of trailing. Right, so now we've got everything we need. We've got the properly calibrated image. We know which one our asteroid is. We've identified all the stars, all the ones that we care about. We still don't know the magnitude of the asteroid because it doesn't really help us. What we look at is we've got a 16-bit image, so we can count the number of counts that are coming out the camera, but it's not going to tell you that that's 10th magnitude. It's just going to say, well, there's 500,000 counts. We need to convert that into magnitudes. So here come the calibration stars. So luckily, in any one field, there's probably about 20 odd stars that have been measured with other surveys, which you can then actually use to lock down the magnitude of your asteroid. So again, another useful bit of software. So this, what's called the Vizier catalog, and this is really quite fun to sort of peruse on those wet evenings. So you can go there and you can look at catalogs, and you can see here it's a little bit small, but it says that here are the calibrated GRIZ magnitude. So GRIZ is G, R, I, and Z band filters. So we were only taking images in the G band, but there's also R, I, and Z band of the Tycho catalog stars. So of course the Tycho catalog stars were originally imaged and they had photometric analysis done in the sort of Johnson band of B and V and U filters. But what these sort of catalog has done, and there's a link to the paper there, is they've taken those original stars and they've converted them into this Sloan set of filters, depending on the filter bandwidth and the original filter bandwidth of the B and V filters and the J and H filters of the Johnson system. So as I said, everyone's got their own set of filters that they like to use, but these are our stars within our field of view. So what we did was we said, well, we know our asteroid is centered at, there you see, 10 hours, 11 minutes and 28 seconds and 14 degrees, 32 minutes, 32 seconds. Tell us all the calibration stars that were within 30 arc minutes of that, which is essentially our field of view. So it's about 1 degree. And you come up with about 22 stars. And we didn't use many of them, actually. It turned out we started off plotting all of them. And it turns out if you start plotting stars with very different spectral classification to the sun, you get quite a bit of scatter in the data. So we found it was actually much better to just pick a star that was close in spectral classification to the sun. Because of course, all an asteroid is reflected sunlight. So why not take a spectral classification of the sun? There isn't one that's quite good enough, but it's close. There's one that's close. You can see here, these are the number of the stars. These are the Johnson filters, what's called the B, V, J, H, and K bands. And then these are the calculated G, R, I, and Z, the GRIS magnitudes. So we were looking in this band here, the G band. There's a whole bunch. The nice thing about this catalog is it tells you which is the spectral classification. So that's an F6, and there's some G05s. That's pretty close to the sun, not quite. There's a G2 somewhere. There's another G05, and I forget where the G2. I've got it on the next slide. So there's a G24, which is pretty close to the sun. So G2V is the sun's classification. So we try to choose something that's pretty close, because of course we're worried that if you start to see the asteroid change in altitude, then you get reddening. So you start to see an effect due to the spectral classification of the object. So you look at the B minus V magnitude and it changes. So it moves towards the red end of the spectrum because of scattering of the starlight. So we chose that was our calibration star. So we use this star, which 11.6 magnitude or 11.64. Red, unfortunately, means it's not really well defined, but it's good within about 0.01 of a magnitude, which is good enough for our requirements. Then we also took 2 reference stars, which I'll show you in the slide in a minute. And they were both G0V stars, so a little bit away from the sun, but not too far. Then we did some aperture photometry. So we do actually have to count the number of well, when you look at the brightness of the object, so we talked about 2 to the 16 earlier with your 16-bit camera. So what we need to do is we need to count up how many ADC counts there are coming from our image. But of course, when we take an image there, and you can see there quite nicely, there's the object, the calibration star. There's the blue circle, and the blue circle is just saying, well, that's a calibration star. The red ones, there's a center circle and an annulus, and this is what we call aperture photometry. So, of course, if we just try to count the number of counts in that circle R1, and we just said, well, that's the brightness of our object, it wouldn't be, because you can see there the sky is not black. So the sky has a background. So we have to get rid of that. So when you do aperture photometry, what you're doing is you're saying, well, okay, I can count the number of ADC counts in the annulus, which is that one there. So what, again, Python and Image Astro J and PixInsight can do aperture photometry. And what you do is you set up an annulus and you count the total number of ADC counts. And you say, well, actually, the background, the best estimate for my background is the number of counts in the annulus divided by the area. And of course, the area is just pi r squared, where you've got R2 and R1 of the relative circle radii. So that gives you a background count, and that's essentially counts per pixel. And then what you do is you say, well, okay, now I count all the counts in green, which are inside my center circle, and that includes this background here. But it also includes your asteroid, and your asteroid is there. So now you've got asteroid counts, you've got background counts, and what you then do is you say, well, okay, I've made an estimate of the background, and I know that because this circle's got a radius of R1, and I've estimated the number of counts per pixel, then I take that average background, multiply it by the area of the center circle, and that's my best estimate for the total background, and I subtract that from my total counts in my circle, and that gives me the asteroid or the reference star number of counts. And that's what you do with aperture photometry. And there's lots of subtleties, so you have to be a little bit careful with aperture photometry. because if there's another star that's sitting in that circle, you can get a skewed image. But because we only had 2 objects, we could actually look for each of the images. And of course, the reference stars don't change. We just have to be careful with the asteroid, that the asteroid doesn't get close to another star in the field of view, which would throw off the estimate. So this is okay for sort of a sparse field. If you're doing this with an open cluster, it becomes much harder. So you have to start masking regions, and your circles don't become quite pure circles. So you can sort of cut them in half and all kinds of weird and wonderful things. But that's the way that we estimate the number of counts. And then, of course, what we've got to do is we've got to say, well, let's convert that into a magnitude. And the way that we do that is we use the magnitude law, so what we call, well, Pogsson's equation. So our students will have learned that in their first year. And what it's saying, of course, is the magnitude system is related to, well, it's a log-based 10 system. So what you do is you take the ratio of the number of counts. So if your star and your asteroid are identical number of counts, and you take the log of 1, you get 0. So then by definition, the magnitude of the apparent asteroid magnitude must equal the apparent star magnitude. But then, of course, if your asteroid has more counts, then it's going to be brighter than the calibration star. And because we know that star was 11.64 magnitude, by looking at the counts of aperture photometry for our calibration star and for the asteroid, we can then actually estimate the magnitude of the asteroid. And that's what we did. And then you just do that for all the images over the course of the evening. So there we go. There's another image of our field of view. So there's our properly plate solved image. So you can see the lines of right ascension, the lines of declination coming across here. There's our asteroid, number 276. There's our calibration star. We also tried to take a calibration star that was quite close to the asteroid. And luckily that was quite close in position, but also in spectral classification. So we did the analysis of that I've just shown you to work out the magnitude of the asteroid. But actually, for sanity check, we also did a couple of reference stars. So we looked at stars nearby, which are the G0V stars, because we wanted to make sure that if we did actually see a light curve, then we really attributed that to the asteroid itself, and it wasn't just due to an artifact, maybe because there was some cloud coming over the image. And of course, if there was cloud, you'd see it in both the asteroid and the reference star. So what we did then was, with Python, the students then just analyzed all those images. So they just put it into a whole loop. It was a little bit challenging to find the asteroid or follow the asteroid because it moves over the course of the night. So they had a little bit of headache trying to track it. But you can actually automate the whole process. So you have a sort of data pipeline that takes in your image, does all the calibration, does the plate solving, finds the asteroid, knows where the calibration stars are, calculates the magnitude, and then plots that to generate your light curve. So that was it. And as I said, we also took the 2 reference stars, and that was really just to check for systematic changes in brightness. And that's the end result. Could have been better, but actually not bad. So, you know, the first thing to note, so there we, on the second y-axis, is our reference star magnitudes. I'm just showing you one of the G0V stars. Both of them were actually also quite flat. So there's 2 nights of data here, and the yellow ones are the first night of the G0V type star, and then the orange ones are the second night of the G0V. And the great thing is that they match up very well. So there's no actual sort of adjustment. This is really, you know, between 2 consecutive nights, there's a very good matchup in the data. And actually looking at the scatter, so what we did was I got the students to look, of course, at the mean of the data. And you can actually put some statistical significance to whether or not you think that you've seen a light curve, because you know your eye's pretty good at looking, and you might say, well, actually, my reference star is not really showing any variation. Kind of wobbles about, but by about 0.01 of a magnitude, plus or minus 0.01 of a magnitude. But then my asteroid, which is this one here, which is the grey and the blue. So what I've essentially done is I've sort of time shifted. So the 2 nights, of course, because it's got a rotation period of 8 hours, you don't necessarily, if you start observing at 9 o'clock on one night and 9 o'clock on the next night, they don't necessarily match up with phase. So all we've done there is we sort of move them in time so they purposely line up, just so we could check the comparison. And actually there's a reasonable good matching. So you can see there, well, there you can see the phase effect. So there's a little bit where there's no blue dots here, and there's a little bit at the end where there's blue dots, because that's the effect of the phase. And you can see here there's a general dip, and then there's a kind of curve upwards, and it drops down again, and then matches, phase wraps around to the starting point there. And this magnitude, well, it's the right magnitude. We'd expect it to be about 10th magnitude. And actually looking at the data values for amphitrite, the magnitude variation is about 0.1, a little bit less than 0.1 of a magnitude. And indeed that scale there goes from 10 to 9, so it's 0.08 of a magnitude. So it's perfectly consistent with the light curve. We don't see any sort of change in the reference star. So looking at it from a statistical point of view, there's quite good evidence that you see a light curve, because if you saw the same effect in the reference star, then you'd say, well, that's due to cloud coming over the image, or it's due to the fact that there's the systematic reddening as the altitude of the asteroid changes, but you don't see it in the reference star. So we think that that is a reasonable set of data. Of course, what we would have liked to do would be to take even more nights of data. So if you can, take maybe 4 or 5 nights of data, then you can just keep overlapping the data. And if you see the same feature appearing night after night, again, it gives you good confidence that you really are seeing the asteroid. Well, I've no idea how long I've been talking for, but I think that's probably about all I've got to say. I mean, I hope you enjoyed the talk. I thought it was quite fun because it brings together a lot of the sort of ideas of what you might do when you're doing data reduction, and it could be anything from deep sky astrophotography, but also for our case here, some of the calibration that you have to do and the stretching. Although we don't do nonlinear stretching, stretching's still an important aspect to get the data. And then I think it was actually quite interesting to do the image analysis with the calibration stars, because I think that really showed the students how you go about sort of statistically verifying that you think that you're seeing a real effect. And the only way you do that is by looking at other known systems where you think there's no modulation. Anyway, I shall finish there, and happy to take any questions.
Great. Thanks, Giles. Perhaps members can thank Giles in another way.
It's good.
Terrific. And you've given me a good lead into some pub quiz questions.
Oh yeah, okay. Probably won't know the answer to any of them, but give it a go.
Right. Anybody wants to submit on Zoom wants to submit any questions on the chat line. If you're watching on YouTube live, feel free to put a question in the comments section, and we'll call them out. So let's just see if we've anything so far. Well, you must have answered everything. So far, we have no questions, but I'm sure there'll be some coming. Anything on YouTube, Will?
Not so far. We've had, just to say, we've had people from USA, Canada, Bangladesh, all over the UK, Romania watching your great presentation, Professor Hammond. And we've also had one comment from Ashkur Raman saying how you've really inspired him with the photography, and he's hoping to further his studies with some PhD in photography. So it's fantastic. Just while I think, I've got a question here. I'm intrigued. You've got a 60 megapixel CMOS camera. You're set up with your triplet refractor 150 Skywatcher telescope. What would be the next thing that you would like to improve your observing potential? What would be the sort of dream sort of setup that you would like?
Yeah, I think actually in terms of many of the projects that we run, we're perfectly well set up in terms of the actual telescope itself. I mean, the plate scale is really good, and the large format camera is absolutely fantastic. I think in terms of doing some high resolution imaging, getting that sort of maybe thinking about how do you get high throughput images, that will be something that we'd like to do, because I think when we run this lab next year, we'd like to offer high resolution imaging. So that's something that we'll certainly try to change over the course of the sort of late summer into the winter. But the combination of mount and telescope and filters really do allow you to do a lot of work. We did, I didn't of course talk about it, but we did do some work with exoplanets. So we had another group of students doing exoplanet research, and that was really tough actually. That was a little bit too hard. So even better quality sky would be good. But we'll learn all about how to do it properly in your talk with Don Polaco. So maybe I should come to that talk and learn all about how to do, like with Super Wasp.
Yeah. Excellent. And just this one last thing, just come across. Do you have any problems with this increase in satellites, that are coming on, affecting any of your images or recording of asteroids? Are they becoming a problem, or are you managing to avoid them so far?
We managed to avoid them. I mean, I've seen awful images of people being really unlucky and get these sort of horrendous constellations of 20 satellites in an image. I mean, I don't think in the course of all the data we took over, it's probably about 4 or 5 weeks. The images we took, I don't think we lost any frames to satellites. So we're either lucky or just in the right obviously right in the right patch of sky.
Yeah, I would define that as lucky imaging, Giles.
Yeah, I think that's another form of lucky imaging. I think there's a few Zoom questions which I'll happily go through. So
yes.
From Neil, I like that as an observation. Yes, maybe writing Python is sometimes easier. I think that the really interesting thing with writing your own kind of software analysis is it's no longer that black box. Sometimes with PixInsight, I mean, it's fantastic, it's really powerful, but sometimes you don't really know what it's done, and it's kind of hard to unpick that. So it says, well, I've done this sort of third order filter fit, and you think, well, that looks really good, but you don't really know how do you optimize that. But if you're writing your own algorithm, there's a much bigger learning curve to start with, but you've got much better control of it. So yeah, I think that's quite a nice observation. And then I see Byron. Oh, excellent, Byron. He's posted a question. So good to see you. Hello.
He's in Colombia at the moment.
Yes. I saw his Facebook post was there. Yeah. Nice
to see you, Giles. Good to see you.
Hi there. Good to see you as well. What do they struggle with? Well, actually, I think it's the software side of things they struggle with. Although we do teach them Python, which I'll pick up with Bruce's question. So we do actually teach them from first year. I'm still surprised that by their 4th year, they still struggle with for loops. Unfortunately, that's probably the hardest thing. And when they get it finally, there's this sort of voyage of discovery and the other thing, as I mentioned during the talk, was when they realized that the asteroid moves, that came as a surprise to some of them. And then, of course, you can use that as a way of saying, well, actually, it's all about looking at orbital elements, and you have to update your orbital elements because otherwise your fit becomes less accurate as time goes by. So I think it is a good learning tool for the students. Practical astronomy, there's nothing better than it, actually.
And you're talking about, I'm just remembering back to our student days of on the software side, trying to cope with, what was it, Fortran 77?
Oh yes, Fortran 77, yes.
And on the observing side, I mean, those observing nights in the Lickey Hills, it's a bit different doing it remotely to Spain. Yeah,
absolutely. Some of the students are really disappointed we couldn't go to the observatory. Well, that's the whole point of a remote observatory. I see there's a question from YouTube, from Will. That's a really good question. Well, with these images, we couldn't really analyze them for spectral content because we just take an image in the G filter. So the G filter is essentially a green band filter with, I mean, it's not a narrow band filter, so it's maybe a 150 nanometer kind of width. In principle, what you could do is we could have taken images in G, R, I, and Z, and then we could have looked at the asteroid in those different wavebands. So we could have done that. Maybe that's something we should do for next year. So that's a nice suggestion.
Okay, and I think John, you had a comment?
Yeah, I was just going to say, yeah, good evening all. The reason, of course, for having two comparison stars is that, like variable star observing, it's not the first time the comparison star has been found to be variable.
Yeah.
So it gives you a cross check against the two. I don't know if that came out of the talk really.
Yeah, that's a good point. It's like having too many GPSs; they all give you a different number. So yeah, you can use it as a cross comparison. Interestingly, we did actually do. I think I'd mentioned it very briefly that we had 22 stars in the field of view. So we did actually start by looking at all 22 of them, and we found that actually that was a worst fit to the data. And I think actually when you start looking at too many stars, then some of them do vary a little bit, and also some of them different spectral classification. So that's why we sort of then kind of went down to a very small number. But there's an interesting extension to the project to identify what's the optimum number of reference stars. So clearly one's okay, but maybe three's better, but 20 is too many. So I think maybe we'll play around with that a little bit next year, more from a sort of statistical point of view.
The famous one, of course, was Polaris. For years, it was a standard reference star, and then it turned into a Cepheid variable, didn't it? So that was a bit confusing for people.
Yeah, absolutely.
Well, thanks, Giles. Look, I'm going to wrap it up there. Can we thank Giles again for a fascinating talk? Thank you, Giles. Thank you very much indeed, and we'll be knocking on your door again before too long, I am sure.
Yeah.
Excellent. I'm going to hand over to Alan now, who's going to talk to us about the sky in July. Over to you, Alan.
Okay, thanks, Andrew. I shall try and share my screen, the right one this time. Right, are you able to see that? Can you see that Sky in July?
Excellent.
Main page.
Yes,
and let me bring up my control screen here.
yes.
Bear with me. Right, Sky in July. Well, of course, a recent highlight was the solar eclipse that we had back in June, and I will report on that. Actually, I'm going to widen the scope of the talk a little bit, not just to include the solar eclipse we enjoyed back in June, but look forward to August and beyond, actually, because we don't have a meeting at which the sky in August is going to be presented. And actually, I'm going to look quite a few years beyond as I get to the end of the talk. That's the star chart for the month as it appears on the Society's webpage and in the Scotsman newspaper, showing the stars as they are at midnight BST in the middle of July. Midnight BST, of course, is not the middle of the night. The middle of the night is closer to 1 o'clock BST. I usually start by looking north, pointing out the Plough and Cassiopeia. The Plough has sailed overhead the last few months, but now it's dipping down high in the northwest, and Cassiopeia, meantime, on the opposite side of the pole star Polaris, is climbing up in the northeastern sky. In the south, well, the summer triangle looks awfully squashed in this projection, but formed by the stars Vega in Lyra, Altair in Aquila, and Deneb in Cygnus. Down in the southeast, the two planets of main interest this month, Saturn and Jupiter, and I'll say a little bit about this area, in particular Hercules, as we go on into the talk. Hercules stands above Ophiuchus and above the star Antares, which in the earlier part of the night is in the south, the bright red supergiant star. That's the data for the sun this month. These times or BST. Nautical twilight still lasts throughout the night at the moment, but by the July 11th, 12th, we started to see the sun dipping more than 12 degrees below our horizon in the middle of the night, so that we can, nautical twilight ends, but we still have astronomical twilight, which will be with us until the sun dips 18 degrees below the horizon. That won't happen until August 8th to 9th as, for observers here in Edinburgh. One other point to point out is that on the 5th of July, the Earth stands at its furthest away from the sun for the year. That distance, 152 million kilometers from the sun. We're 5 million kilometers further away from the sun than we were when the Earth was at perihelion in early January. And I show the moon phases. A new moon is coming up on July the 10th. Of course, when the moon was last new on June the 10th, then it passed in front of the sun. And if you're in the right place on the Earth, you enjoyed an annular solar eclipse. We in Edinburgh saw a partial solar eclipse at mid-eclipse, not very far away from when I took this picture. The moon covered 43% of the sun's diameter. This is an unfiltered image of that event. Passing clouds affected for many of us, but also many members did obtain images and posted them to the ASE's Flickr pages. And of course, Mark Phillips live streamed his view of the eclipse. These are some of the images. I couldn't show them all because there are too many. So I picked out one from 7 different members showing their views of different stages of the eclipse. I did a timeline of the moon passing across the northern part of the sun, and other people did the same sort of thing. This is Horst's view from Kiel in Germany, where the moon covered 30% of the sun's diameter compared with 43% for Edinburgh. And we also had sets of images from Pat Devine and from Will Joy. Looking ahead on the eclipse front, well, we've got a total lunar eclipse during the early morning hours of May the 16th next year. That's our next main eclipse. There's another partial solar eclipse for us on October 25th next year, when we'll have 31% of the sun's diameter hidden. I'm talking about the sun. There have been a few more sunspots of late. This is one by John Watson, or an image by John Watson showing a group of spots. The main spot is sunspot AR, active region 2833. Nigel Goodman got this nice full frame view of the sun earlier in the month, June the 2nd, again showing a prominent sunspot. And John Watson again posted an image on our Flickr group, Flickr pages, of a sunspot taken just yesterday. And that's very nice. It shows these granularity convection cells on the sun's surface. These cells are hot rising gas, and each of those granules is about 1,000 kilometers across. That gives you the scale of the thing. And people who have not just been looking at the sun, we've got several images of the moon. Radim Stano has obtained this image of Ptolemaeus as a large lunar crater. Ptolemaeus, 154 kilometers across. That crater above it is Herschel, and below it, with a central peak, is the crater of Alphonsus. There is a crater called Ptolemaeus B, and you can just see it. It's a ghostly ring in the northern part of Ptolemaeus. It's a lava's flowed over what was obviously an earlier crater. And that's just north of this smaller crater, which is the crater Ammonius, which is 9 kilometers across. Radim has also obtained this image of Plato and the crater Plato, flooded crater Plato, and the Alpine Valley cutting through the lunar Alps. Plato is 110 kilometers across. The Alpine Valley is 166 kilometers long and up to 10 kilometers wide. And I've picked out a couple of interesting features on this image as well. 2 of the moon's standalone mountains on the moon are not that common, but 2 of them are in this image, Pico and Piton. Pico is one of the objects in the ASE's Lunar 100 project list, as was Ptolemaeus and the Alpine Valley. Pico and Mons, they're really called Mons Pico, Mons Piton. They're isolated mountains. They rise, well, Pico's the slightly taller one, 2,450 meters, kilometers. No, I'm wrong, obviously, 2,450 meters above the plane. The other one, Piton, is a little bit lower, 2,250 meters. Both of them are about 1,000 meters higher than our Ben Nevis. So it gives you an idea of scale there. Looking at the planets for July this year, for this month, the sun is now starting to sink downwards in celestial latitude or declination. It drops 5.1 degrees south during July as it moves from Gemini into Cancer. And preceding it in the sky and getting ahead of the sun is Venus, which is brilliant, but very low in our west-northwestern evening sky. At sunset, you may have to work hard to see it. And even harder to see and quite close to Venus is Mars. These are the relative sizes of the two planets at the middle of the month. Mercury is on the opposite side of the sun, the morning sky. That also has a period of visibility this month in the northeast before dawn. But the two bright planets in the evening, visible for much of the night, are Saturn and Jupiter. They now rise before midnight, in fact, shortly after sunset in the middle of the month, as they approach opposition in August. Looking north at midnight BST on July the 16th, well, the plough is here, sinking down in the northwest. Cassiopeia is over here, climbing in the northeast. Here's Polaris, winding between the plough and Polaris, and the constellation of Ursa Minor is this long constellation of Draco, with the head of Draco nearly overhead at this time of year. Leo is setting over here in the northwest, and in the northeast we have, and east, we have the square of Pegasus and Andromeda starting to become visible again. But of course, something to look for in the northern sky at this time of the year. We're still in the season for seeing noctilucent clouds in this region of the sky. This is the view from the Isle of Skye on May the 26th, and you can see lower level clouds in darkness, but the blue noctilucent clouds becoming visible. They stand at around 82 kilometers above the ground, and they're visible when the sun is between 6 and 16 degrees below the horizon. They're often bluish silver, and they reflect sunlight when the lower level clouds, these sorts of clouds, are in darkness. And they're normally seen from mid-May to mid-August. And during the last few weeks, there have been a few displays, and the clouds of noctilucent clouds have stretched southwards. That was a view over Paris on June the 18th, with the noctilucent clouds visible and these lower level clouds in darkness. Looking west in the middle of the night at mid-month, or at midnight BST at mid-month, that's the view we have. The brightest star in the west at this time is the star Arcturus in Boötes, found, as you know, by extending a line along the handle of the plough and then onwards past Arcturus to Spica, arc to Arcturus, and spike to Spica. So the story goes. There's the head of Draco pretty well overhead, and Hercules high in the southwest above Ophiuchus, and Antares in Scorpius down here. But the evening sky, earlier in the evening, if we look west, we have a chance of seeing Venus, a small chance of seeing Mars too. These are the three views of beginning, middle, and end of the month. 45 minutes after sunset, looking between the west and the northwest. And if you compare the positions of Venus between the three diagrams, you'll see that during the course of the month, 45 minutes after sunset, Venus is gradually getting lower, which is surprising because Venus is actually pulling away from the sun, but it's also stretching southwards from the sun, and therefore it's not as high in our western evening sky. These are the two relative sizes of Mars and Venus at the middle of the month. Both of them are, if you had a telescope and you could see such small objects so low down, both of them would appear as small, almost full disks, but very small. Actually, Mars passes half a degree south of Venus on the 13th, but it's already difficult to spot in the twilight, and I've got my doubts about whether you'll see it at all easily this month. The moon, by the way, is 5 degrees above left of the pair of planets, above left of Venus and Mars on the evening of the 12th. The moon at that time will be 8% illuminated. Let's turn our attention to the south at midnight and mid-month. Summer triangle, here it is, reaching the meridian high in the southeast. The line down the western edge of the triangle, Vega through Alta, points onwards to Saturn, so you can find Saturn. And if you go look to the left of Saturn, roughly the same sort of elevation, you have the even brighter planet Jupiter. Hercules is very high in the southwest. And of interest is the fact that another nova, we had one a few months ago, but this one flared in Hercules in June, in fact on June the 12th, just a couple of days after the eclipse. It lies right in the southeastern corner of Hercules, and that's the position of it. Hercules you wouldn't expect to stretch into this region, but that's where nova Hercules occurred, found by a Japanese astronomer, magnitude 8.4 when he found it, but it brightened, and it had brightened from fainter than magnitude 13 2 nights earlier. Within a couple of hours of him finding it, it was already a naked eye object at magnitude 6, and it then began to fade. And if you plot the brightness of nova Hercules, then that's the plot you get. This was the 12th of June, and this was yesterday or this morning, down just below magnitude 13. Observations by the American Association of Variable Star Observers. It's now about magnitude 13.1 and falling. And this is a fairly typical light curve for a nova. It's nothing like the light curve of the other nova that I mentioned earlier, which I'll come back to. Let's now focus more closely on Hercules, or in fact this region between Vega and Arcturus in the high north southwestern sky at midnight. And that's it blown up with a few interesting objects added. It contains 2 of the brightest stars in the night sky, Arcturus, I've already mentioned in Botes, and Vega in Lyra, Arcturus being the 2nd brightest star in Scotland's night sky, and Vega being the 3rd brightest star in our sky. If you join them, then that line is quite interesting because it cuts through 2 interesting asterisms. Well, first is the constellation, the Corona Borealis, the northern crown, and the second is this quadrilateral in Hercules, which we call the keystone. And if you look close to the western edge of the keystone just here, you have the famous globular cluster M13. Here it is photographed by Nigel Goodman. This cluster is about magnitude 5.8 at the verge of naked eye visibility. Looks like a fuzzy blob in binoculars. It was discovered by Edmund Halley. It's 23,000 light years away, and the stars in it are that far away. It has a mass around 600,000 times that of the sun. And it's about 11.65 billion years old, so it formed not long after the beginning of the universe. 6 degrees north of the keystone up here is M92, and that's another photograph taken by a member. M92 is another globular cluster, magnitude 6.3, so fainter than M13. It's also further away, 26,700 light years, and it gets far more attention, I think, were it not for the fact that it was outshone by M13. It's fewer stars, 200,000 stars, it's thought, or 200,000 times the mass of the sun. And it's about 11 billion years old. Let's clear up our view to pick out a few other interesting objects. The 2 brightest stars in Hercules are these 2, Zeta and Beta Hercules. Beta Hercules is sometimes called coniferous, which means club bearer, or rutilicus, which is a corruption of the Latin for armpit. And that beta is a spectroscopic binary with 2 stars orbiting each other every 13 months or so. Now, Alpha Hercules is not joined up by any of these lines at all. It's this star down here, Ras Algeti. It's 360 light years away, about magnitude 3.1, and look at it through a telescope, and it's a nice contrasting double star, orange and whitish stars, 4.6 arc seconds apart, which orbit each other every 3,600 years or so. The fainter of the two is magnitude 5.3. The brighter is a variable star, and it occasionally reaches magnitude 2.7. So it can actually become brighter than Zeta and Beta. It's been pretty stable about magnitude 3, but I've just noticed in the last few weeks, I'm told it's slightly fainter, about 3.3. So it may be starting to fade. Russell-Jethy is a multiple star. The primary is believed to be a close binary itself at the limit of visibility. And the secondary is definitely a spectroscopic binary with the 52-day period. So there's at least 4 stars involved with that system. Russell-Hague is the brightest star, is Alpha in the constellation of Ophiuchus. Its name comes from the Arabic for the head of the serpent collector. It's magnitude 2.1, considerably brighter, about as bright as the stars of the Plough, and it's a binary 2 with an 8.6 years orbital period, and it lies 49 light years away. In the top left corner, we've got an interesting area of constellation Lyra, so I'll focus in on that now. There is a close-up of it. Several things to look at here. First is M56, and that's yet another globular cluster. Hugh Somerville produced an image of this, good deal fainter, magnitude 8.3, so you'll need a telescope to view it, 32,900 light years away. And the story goes that it's 13.7 billion years old, but since the Big Bang was thought to be 13.8 billion years ago, you've got to take the age with a pinch of salt, I think. Not so easy through binoculars. Its core is less condensed. The next object of interest is M57 down here. That's the famous Ring Nebula, planetary nebula, which appears to be 1.5 by 1 arc minutes across. Magnitude 8.8. Through binoculars, it appears like a faint star. You really need a telescope to see it as this sort of ring. The ring is expanding at the rate of 1 arc second a century as material flows away from the central star, which is now a white dwarf. Right in the middle of the ring is a white dwarf, the remains of a larger star that shed its outer atmosphere. The light that we see comes from ionized hydrogen, oxygen, nitrogen, and sulfur. And the HST, the Whole Space Telescope, shows a much greater extension of the nebula out to about 4 arc minutes. Obviously, early materials shed from the star. Of course, you probably know that there's a problem with the HST at the moment. It's some sort of computer issue, and it's been offline and not working properly for 3 weeks. They still hope to make it recover by perhaps switching to backup systems. The final object I want to mention in Lyra is the famous double-double Epsilon Lyra, which is again shown in an image by Hugh Somerville. Binoculars, even the naked eye, you can see it as 2 stars if your eyesight is very good. The main ones are 2.5 arc minutes apart, and they're easily seen through binoculars, sometimes with the naked eye. Each of these is itself double and about 2.3 arc seconds apart in each case, and that's an image by Tom Kerrs. And if you look carefully, you can see the diffraction spikes from the 2 stars in each of these pairs. One of those stars is also a binary, but it's too close to be separated by normal means. Let's look in the southeast, because that's where we've got Saturn and Jupiter. And if you plot the paths of the 2 planets during the course of July, you end up with these arrows, quite short arrows in Aquarius and Capricornus. They're both creeping westwards. They're doing a retrograde motion. By far the brightest of the 2 is Jupiter, which is magnitude minus 2.7. In fact, that's minus 2.7 in mid-July. During the month, it brightens from magnitude minus 2.6 to minus 2.8. It's 47 arc seconds across, so you'll quite easily see it as a disk through any telescope. And you'll also be able to see the belts and zones and spots. And you can obviously track the motion of these during the course of the night because they move across the disk from side to side. The moons are also visible if you've got binoculars and you can keep them steady, perhaps using a tripod, then you can see the moons rather more easily. They're obvious through a telescope, and Jupiter is at opposition on August the 20th. So that's when it stands directly opposite the sun. So it rises at sunset. It's highest in the south in the middle of the night, and it sets at sunrise. Saturn is several moons visible telescopically, but the main attraction, of course, is the ring system, which is now slowly closing up as the North Pole tends to tip away from us. Side to side of the rings, it's almost as wide as is Jupiter, so it's quite easy to spot the rings through a telescope. And Saturn reaches opposition as early as August the 2nd, so we're just a month away from Saturn coming to opposition. Let's look east at the midnight time on July the 16th. Here you see Saturn and Jupiter slightly to the right of due east. And here's the summer triangle high in the southeast. Rising, climbing above the eastern horizon is the square of Pegasus and the constellation of Andromeda, where we have the famous Andromeda galaxy M31. You may recall that earlier this year, I went on a bit about a nova discovered in Cassiopeia. This is the year's other nova, a nova discovered by another Chinese astronomer, Nova Cassiopeia 2021, which is also now called V1674. Well, it's not called V1674 Hercules, that's wrong. It's V1405 Cassiopeia. That's an error on my display. That's been a very interesting nova. Instead of just fading away as most novae do, it's varied in brightness quite considerably. This is the initial brightening to about magnitude 7.5. And then it's hovered around that brightness, got slightly brighter, and then had a sudden increase in brightness in May when it reached magnitude 5.2 or so, which, would it not be for the twilight that we had, it would be a naked eye object, and many people could have seen it by naked eye in other parts of the world. Then fell back to roughly the same brightness as it was, and since then it can't make up its mind whether it wants to brighten or fade. And these are the brightness reports of it from this morning, back more or less where it was when it was discovered. So, well, you place your money on what will happen next. Is it going to brighten again, or is it going to fade away? We don't know. Let's look at the morning sky now. This is looking low in the northeast at 3:54 BST on July the 8th, which is 45 minutes before sunrise. The sky is very bright. You may not be able to see any of the stars down here, but there is Mercury, and it's a difficult morning star for a couple of weeks. This is the view on the 8th, that's next Thursday, and the moon is not far away. The moon's a very slender crescent. There it is, only 4% illuminated. Mercury rises, in fact, more than 75 minutes before sunrise between July the 8th and July the 20th. And between those days, it brightens from magnitude 0.1 to minus 1.1. It's actually been, or being, furthest from the sun on the 4th of July, but it's still, at that point, it's too low to see easily from Scotland. And that's the appearance of Mercury on July the 10th, when its phase is roughly half and half, 50% sunlit, 51% sunlit, and 7 arc seconds across. So still quite a small object to view in our morning sky if you feel like getting up at 4 o'clock in the morning. Now let's look ahead into August, because as I mentioned, there won't be a meeting to show a sky in August talk, because August has a very good meteor shower, the Perseids, and at that date on August the 13th, the shower is at its best, the greatest rate of meteors, and they all diverge from a Perseids radiant, which lies roughly between the main stars of Perseus and Cassiopeia, just about here. In fact, during the course of a few weeks, that the meteors are still visible, but the radiant itself moves. It starts off somewhere up here, just to the south of Cassiopeia, and ends up down here a month later. The shower itself lasts from about July the 17th, so I guess we can include it in a July talk, and it goes on till August 24th. The peak, though, is on August the 12th, just a few hours before this map is drawn for, and is predicted to occur at about 8 p.m. BST, which time is daylight for us. Fast meteors, rather, 59 kilometers per second, and they have trains, which means that they leave a trail of material in their wake, ionized outer Earth's atmosphere in their wake, which slowly fades away. And the zenithal hourly rate, the rate at which number of meters you would see in an hour, if you were under a perfectly dark sky, is expected to be more than 80. Well, other things can affect that, such as street lighting and light pollution, clouds, obviously. But you'd be lucky to get rates of even half that would make an interesting display. And unfortunately, this year we have very little moonlight interference. The moon is a very early evening object and not very bright. The meteors of the Perseus meteor shower are once called the Tears of St. Lawrence. It's said that his martyrdom occurred around this time of year. He was burned alive on a grid. Comet Swift-Tuttle is the parent comet. The meteoroids that cause the meteors are debris from Comet Swift-Tuttle. Comet Swift-Tuttle has a 133-year orbit of the Sun, and it last reached perihelion just inside the Earth's orbit in 1992. And this is looking south at midnight on that day. That's that time. And at that time, midnight in mid-August, the summer triangle is high in the south with the Milky Way cutting through it. Saturn and Jupiter are getting towards the south. They're reaching opposition. There are lots of interesting stellar sites in and around the summer triangle. We've already mentioned the Dumbbell Nebula. Sorry, I've already mentioned the Ring Nebula, but we also have a Dumbbell Nebula in Vulpecula, which I think is around here. Inside the summer triangle, the Dumbbell Nebula, M27. Also Albirio, which is the star at the end of this of Cygnus, the beak of the Swan, which is another well-known double star. I want to draw attention to a star in the center of Cygnus, which is just here. There's the summer triangle. The star Satyr, because Pat Devine obtained a super image of this region. There's the star Satyr, showing lots of gaseous material in this part of Cygnus. Satyr is a bright yellow-white supergiant star, and it lies around 1,800 light years away, so it's not very dissimilar to the distance of Deneb. And it's thought to be only around 12 million years old. It's 150 times wider than the Sun, and surprisingly, its surface is almost exactly the same temperature as the Sun, 5,790 degrees Kelvin. It's 12 times the mass of the Sun, and all that adds up to 33,000 times as luminous as the Sun. This image was obtained by Pat Devine as recently as May the 28th, showing that with skilled photography using special filters, it's possible to obtain stunning astrophotos, even under bright twilight and, in this case, moonlight conditions. The material you see here is glowing gas. It's a Mission Nebula. The gas is ionized gas, emits at different wavelengths, hence the different colors. And the energy for that comes from ionization of the gas by hot stars around it. Now, I said I wanted to go even further ahead. This is an image from 2017 October, when this comet 2014 UN271, or called Bernardinelli-Bernstein, was discovered by astronomers Pedro Bernardinelli and Gary Bernstein, both at the University of Pennsylvania. This comet is shown as a tiny dot on this image taken in 2017. The first image of it was obviously taken in 2014, and that's the designation of an asteroid. And it's only more recently they've realized that this is moving along an extraordinary orbit, and that it must be a very large comet, in fact, at least 1,000 times more massive than your typical comet, and probably the largest comet that's ever been discovered, or been discovered in modern times anyway. Estimates suggest the favored diameter suggested by is about 160 kilometers, which compares with 5 kilometers for Comet Halley, the nucleus of Comet Halley. In fact, the true diameter of this comet could be anywhere between 100 and 370 kilometers. Early observations showed no evidence of a coma or tail. It was just a moving point of light. But recent observations do show that there is a faint diffuse coma around it, gas and dust, perhaps released from the surface. There's an artist's impression of what it might look like. Currently, it's only 20th magnitude, and it's in the far southern constellation of Horologium, which is the constellation of the astronomical clock. It lies 51 degrees south of the celestial equator. And let's take a bit of note of where it comes from. Most of the things like we've been observing recently, like Pluto and other distant objects, lie in the Kuiper belt, which is about 40 astronomical units away from the sun, 40 times further from the sun than is the Earth. These are meant to represent the planets, but they're not to scale. The distances are not as evenly spaced as that. Much further out is the Oort cloud. That lies about 1,000 to 100,000 astronomical units from the sun. And the long period comets tend to dive in from the Oort cloud in towards the sun as an orbit of a long period comet. This one, the one we're talking about, that's been recently discovered, is thought to have an orbit that takes around 5.5 million years to go around the sun. And that's the plot of it from the JPL small body database. This is the orbit of the comet. That's where it was yesterday. It's heading this way. It's due to reach perihelion, its closest point to the sun, not until 2031, January the 23rd. And at that point, it'll be 11 AU astronomical unit away from the sun, still beyond the orbit of Saturn. Saturn average is 9.6 AU. The comet is moving in a retrograde orbit, 95-degree inclination, slightly retrograde. And it's at the moment 51 degrees south as we see it in the sky, and it's diving further southwards. It's by 2027 it reaches 76 degrees south declination, but it then starts to climb northwards. And if you wait until after perihelion in 2031, then it possibly will become visible in Scotland near the end of that year. People are considering how bright it might get. Some people say it may become visible in small telescopes. Others say it may not get brighter than magnitude 17. There's also a great deal of interest in opportunities for it passing in front of stars, the nucleus passing in front of stars, which will give a direct measurement of its brightness by using occultation to give an exact idea of its size. But you need a really accurate orbit for that, and still working on improving that orbit. That's something to look forward to in a few years, in 10 years' time. Right, and that's the end of my presentation for the sky in July. Thanks so much.
Well, can we thank Alan? That was a great presentation, as always.
Thank you.
Very wide and very deep.
Alan.
I can't help but think, if I to talk to my grandchildren about looking at a star called Armpit, they'll think it's hilarious. But anything that encourages people into astronomy, I don't mind. It's great. Well, a fascinating evening. Thanks, Giles, and thank you for staying. I hope you enjoyed that. We look forward to hearing your next talk on either of the subjects we've discussed in the not too distant future. Next Wednesday, for members, it's the Imaging and Observing Group, as we know. So I look forward to perhaps seeing you then, although I may be away and I may get a connection